problem. Again, part C here, a ladder 25 feet long leans against the wall of a house. Here's our ladder. The base of the ladder is pulled away at 2 feet per second. How fast is the angle between the ladder and the wall changing when the base of the ladder is 7 feet from the wall? So identify your angle. Your angle we're talking about right here is this one up here at the top at Y. And we're going to call that theta. Theta, Greek letter commonly used to represent an angle. And in this case, we have to look for some sort of relationship between the angle theta and the sides of your right triangle, which means we're going to need to utilize one of our trig functions, sine, cosine, or tangent. And the truth is, any one of the three is usable. I would caution against tangent. And the reason I caution against tangent is because, remember, sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. So our opposite side from our angle would be the x dimension, and our adjacent side would be the y dimension. And both of those are changing dimensions in our problem. So we would end up with tangent theta equals x over y, which would require us to do a quotient rule, which would be a longer, more complicated derivative than is necessary. If we pick sine or cosine, both of those involve the hypotenuse, which means part of our derivative or part of our equation is going to be a constant. We're going to be able to plug that in. So you can see I can set this up here. I have sine theta is equal to opposite of our hypotenuse. Then I substituted in that the opposite side from our y angle is the x dimension. And the hypotenuse is 25 feet, and that's a constant, so I plugged that in. I've rewritten that a little bit as sine theta equals 1 over 25, and again, 25 is a unit of feet, times x. And the reason I did that is because now we're looking at a very simple linear derivative here. We've got a constant times an x value. That's going to be a very, very simple derivative for us to do. Again, we're still dealing with this point in time when we're 7 feet away from the wall. So our x value is 7 feet. Our y value then was 24 feet. And the dx dt 2 feet per second was given information. Keep in mind, both of these are changing dimensions. We plug them in at the end. So let's go ahead and take our derivative. And again, we're taking a time derivative. So I'm going to start with d over dt. And we're taking the derivative of sine of theta equal to 1 over 25x. And that derivative, the derivative of sine theta, will give us cosine theta. And don't forget, theta is not a time. So that is going to be multiplied by a rate of change, d theta over dt. And that's important, and I didn't write that down up here, and I really should have. D theta dt is what we're looking for in this problem. So I'm going to go ahead right now really quick and put that down. We are looking to find the rate of change of the angle theta is what we're looking to find. So in our derivative, we get cosine theta d theta dt, and that's going to be equal to 1 over 25, because that's our constant coefficient, and the derivative of x with respect to time, which is just going to be a dx over dt. So we have excuse me, everything we need to plug in now. We know dx dt, but we got to think of what we're going to plug in here for cosine theta. And remember, theta is this angle up here at y. Theta is or cosine is defined as the opposite side, correction. Cosine is defined as the adjacent side divided by the hypotenuse. Well, since our adjacent side is y and our hypotenuse is L, we know our y is 24 and our hypotenuse is 25. So what we're going to do here, and I'm going to go all the way over here and line it up with this, we're going to put in a new equation. Instead of putting in cosine theta, we're going to put in the fraction of 24 feet over 25 feet times d theta dt and that will be equal to, we're going to plug in our values over here and we're going to have fraction 1 over 25 feet times another fraction. As we plug in dx dt, remember that is 2 feet over seconds. Now, take a look at what's going to happen here with our units. We've got feet over feet on this side, we've got feet over feet on this side, and all we're going to be left with is this second in the denominator. When all those units of lengths cancel out, our remaining leftover unit is going to be what we call radians per second. So, to simplify this from here out, all we're going to do is we're going to divide this fraction over to this side of the equation. And we're going to remember, when we divide our fractions, that is equivalent to multiplying by a reciprocal. So once we divide that over there, we'll have d theta over dt equals 1 over 25 times 2 feet per second and I'm going to get rid of those units for right now. 2 over 1 times the fraction that was our cosine, which is now going to be 25 over 24. And I'm going to put a unit here at the end of radians per second. All these feet units are gone. The feet have canceled out. Feet over feet, all canceled out. We're left with these three fractions multiplied together, which is pretty simple because the 25 and the 25, they're going to, I wonder if we can do this in here. Let's see. It won't let me it won't let me do that. I was going to do a strike through on the 25s. 25 and the 25 will cancel out. We'll be left with 2 times 1 and 1 times 24 and 2 over 24. We'll throw that in as a fraction first. 2 over 24 equals fraction of 1 over 12. And our units are radians per second. And that is our final answer, 1 over 12 radians per second. Now think about it. If the bottom of this ladder is sliding out and the top is sliding down, this angle theta should be getting larger. If it's getting larger, we should have a positive rate of change, which we do see here. So that's telling me we've done everything correct. So I think that's a pretty simple problem. Again, it would work if you chose cosine. You would just end up with a different fraction here. Yeah, pretty straightforward problem. Common example of a related rate right triangle problem. So I hope this helped, and check back soon for another example.